I would like to start this week by sponsoring Starbucks. In order to make these videos, it needs to be 100% dark in the room, which means I need to wake up at the very early hours of the day before the sun has risen. And this is the only thing that makes me not look like a zombie right now. So thank you, Starbucks. Okay, this week we're going to be applying all the vector mathematics that we learned last week into the world of two-dimensional and three-dimensional kinematics, okay? So we're going to take all the motion stuff that we learned 2 weeks ago, right, and revisit it, understanding that now motion can happen in 2 dimensions. And the most classic example of that is what we call projectile motion, when you have something launched into the air, like a little ball here, right, launched into the air, and then that lands at some other spot, right? That's projectile motion. Turns out there's quite a bit of that in the real world. Anything operating under a gravitational field undergoes projectile motion. So without further ado, we'll move on. So if you guys can move to the why do we care slide. This is really, really interesting. Apollo astronauts took a 9-iron to the moon and hit a golf ball a maximum range of 180 meters. Okay, that is a really good drive, and it happened because it's the moon, right? So assuming that the swing, launch angle, and so on were the same as on Earth, where the same astronaut could hit it only 32 meters, could we find the acceleration due to gravity on the surface of the moon? After this lesson, you may be surprised to find out that you can solve this. And we'll get there. We'll get there. Okay, so if you guys could advance to the quote of the week. This is one of my favorite fellows, just an affable Indian fellow who passed away in the 1980s. His name was Anthony DeMello. And he has this saying that says, "Don't ask the world to change. You change first." This quote reminds me a lot of voting. You know how like you're like, my vote doesn't really matter. I'm only one person. I can't really sway an election. But if everybody thinks that way, then you're right, you won't sway an election. But if everybody does vote, all those single votes add up to what could be possibly major change, right? I think it's the same for changing the world, right? If all of us decide to change the world all at the same time by changing ourselves, then whatever just increase in compassion and reason that we have in our interactions will just cascade and multiply. So yeah, if we all made that decision at the same time, we're the most powerful people in the world. All right. If you guys could advance to the next slide, which says grown-up physics. So in the real world, stuff happens in 2 and 3 dimensions, right? Sometimes things do happen in 1 dimension. Sometimes you do have just a train accelerating in one line. Sometimes you do have a ball just falling perfectly straight. But in the very majority of cases in the world, you have things happening in multiple dimensions. You have projectile motion, as I've shown here. Okay. So now we can use vectors to actually describe that motion in more than 1 dimension. All right. Let's start out with the basics. We want to start out with the position vector. Okay. So the position vector is usually represented with an R, right? And it's your x coordinate I. No big surprise there. Your y coordinate j, and your z coordinate k. Okay, so if I have a Cartesian plane, right, that's like, y, x, and z, right, then this would be, however far I go x in the I direction, however far I go y in the y direction, and then however far I come out in the z direction. Okay, and so if you advance one more slide after that, there's a specific example where we have r equaling -3i plus 2m. Sorry, that's meters. I'm just going to ignore the meters for now. J plus 5k. Okay? And if I want to put that in a Cartesian plane, use a different color here. I have an x and a y and a z again, right? Then I am just going to be going -3 in the x direction. So I go 1, 2, 3, right? +2 in the j direction. So 1, 2. And then +5 in the k direction. So 1, 2, 3, 4, 5. Right? So my vector would then start at the origin and wind up over here. Okay? That is my position vector. And this is my location in 3-dimensional space if that is my position vector. Okay? So far pretty basic. It's just like putting a point on the Cartesian coordinate plane, except instead of a point, it's an arrow pointing to that point. All right? Not too crazy. So that brings us to the next slide, which is the displacement vector. Okay? So to get displacement, your displacement is simply your change in position vector, right? So your displacement is simply your final position minus your initial position, okay? Which is the same thing as saying whatever is your x2, your x coordinate for the r vector, your r2 vector, minus x1, I, right? Plus y2 minus y1, j. And if it's three-dimensional, you'll have the same thing for the k direction or the z direction as well. All right. What is this? This is subtracting two vectors, right? This is what we learned. This is why we learned it last week, right? How to subtract vectors and how to add vectors. But the displacement vector is simply the difference between two position vectors. So if let's say this is my r1 here, and let's say that I have another r2 over here, right? Then this here would be my displacement, which is r2 minus r1. OK? All right. So if you guys could advance one more slide, it says a rabbit running through a prairie. We're going to do one example of a problem that kind of adds some flesh to the bone, makes this a little bit more clear and understandable and less abstract. OK? So I'm going to erase this guy, make my funny faces for the day. OK. I should start coming up with like questions to ask while I'm erasing, because it's kind of like an awkward pause. But maybe it gives you guys a little time to just, think about things, make some sense of what we just talked about. OK? All right. Here we go. So we have a rabbit running through a prairie, OK? And the thing about this rabbit in this prairie is that we have some coordinates that are a function of time, right? So the x coordinate of this little rabbit, right, is going to be, so I'm going to put rabbit over here, the rabbit problem. Okay, the x coordinate is negative 0.31 t squared plus 7.2 t plus 28. Okay, and the y component as a function of time is 0.22 t squared minus 9.1 t plus 30. All right. All right, that means that at any given time that I put in, I can find the x and y coordinate, right? And as a result, I can obviously find the position vector, because the position vector is just xi plus yj, right? So the first problem says, what is the rabbit's position at t equals 5 seconds? OK, all I would do then is put in 5 seconds for t here and 5 seconds for t here. I'm not going to take the time to write in 5, because it's easy, right? Just put in 5 for both of those. If you want, pause, put it in your calculator, check it out, see what you get. I get, for r equals 5 seconds, I get 56.25 I plus, so not plus, minus 10j. OK? That's what I get for my position vector at 5 seconds. OK? And so, if I'm in a Cartesian plane, then that's going to be like, 10, 20, 30, 40, 50, 6 minus 10. So I'm like right there. This is my R5, right? And so, yeah, so just to be clear, these positions, this is the position of the rabbit as a function of time. So at 5 seconds, the rabbit is in this position right over here. Okay? Now, it says, what is the rabbit's position at t equals 7 seconds, right? All right, well, let's do that. So we want r at 7 seconds, right? I, again, put 7 seconds into my x and y here for the t's, and I get 63.21 I minus 22.92 j. Check me if I'm wrong, but those are the numbers I'm getting, right? Which means that now at 7 seconds, I'm in a position of, well, this is 10, 20, 30, 40, 50. Let's go 60, a little bit beyond that is 63. And then now I'm minus 10, 22, right? So my new position is over here at r equals 7, okay? And so I want to know, what is my displacement, right? How far am I from where I ended? And so that's number 3. What is the displacement for the rabbit for its motion between 5 and 7 seconds? Okay, well, we know, ladies and gentlemen, that all you need to do is take your r2 minus your r1, right? In this case, our r2 is actually r 7 seconds, right? R at 7 seconds minus r at 5 seconds, right? And we would get x2 minus x1, that's 63.21 minus 56.25. I, right? Plus, now we want a j, which is going to be negative 22.92 minus a minus 10, which becomes plus 10, j. Okay? And when I put all that into my calculator and I do my subtractions, I get a displacement, right, sometimes called delta r, of 6.96 I minus 12.92 j. All right, that is my displacement vector, and now I know from this I can calculate how far I've gone, how far I am. How do you do that? Well, remember Pythagorean theorem. You find the magnitude of this. It's this guy squared plus this guy squared, square root, right? And if you want to find the angle, the direction at which you've actually moved from where you started to where you ended, it's going to be inverse tan of this guy divided by this guy. Okay? So that is just one quick, early, simple example of how we would use position vectors in 2 dimensions. Okay? In the next video, we're going to extend this to velocity and an instantaneous velocity, and then we're going to look at some projectile motion. Okay? I'll see you there.